Time is 1:58. So we got a minute and some change still. Right, so especially for those of you who just got out of that test, intermediate calc 2, y'all ready for the daily quiz? So key for this one today. Remember how to get the characteristic equation from a differential equation. I should put the S in parentheses because as we saw, there might be multiple roots, there might just be one root. Put the S in parentheses on roots. So I should. There might be one root, there might be two roots. I'm not asking you to solve the differential equation. Okay, I'm not asking you to solve it. Just find the roots of the characteristic equation. Check answers. Maybe 30 more seconds with the answers. All right, 10 seconds. If you're trying to type it in at the last minute, all I need to do is give me the number and or numbers. You don't have to do any special formatting or anything to it if you don't want to. All right, so if you got everyone in, so locking answers here in 5 seconds in case you want to change. 4, 3, 2, and 1. So first question, how do we get the characteristic equation? From this differential equation right here. I know how to do it. I know that's all two right answers in there. How do we get characteristic equation from a differential equation? Sorry, second order homogeneous differential equation with constant coefficients. And also linear. I didn't say linear. It's really simple. Take coefficients on the differential equation. Right? Replace the second derivative with r squared, replace the first derivative with r, and then just take the coefficient for whatever the y term is. And then the roots of this, we're going to end up being what I needed for my solutions, because we said our solution should be something in the form, some constant times e to the RT, where r is coming from the solution here. Like I said, all I wanted you to do was figure out what the roots of this characteristic equation are. Well, I need to factor it. What does this factor into? R minus 1 quantity squared. So then this is going to be equal to 0 when r is what? 1. Are there 2 roots here or 1 root? Just 1. Until you get 1 repeated twice, but there's only going to be 1 unique value. And then we weren't asked this for the daily quiz. But this just tells me then that the solution to this differential equation, because it's linear, second order with constant coefficients and is homogeneous, is just some constant times e to the RT. If you plug that solution into the differential equation above, take its second derivative, subtract 2 times its first derivative, and then add itself, you'll see that it will add up to 0. So what questions do you have? I see something brewing. You just came out of a test. You can forgive yourself. All right, so we're going to keep moving on. We're just going to do this again. Make sure we see this process of, as long as I'm giving a second order homogeneous linear differential equation with constant coefficients, how I can get the solutions. So let's do a new one. You good, Xavier? Guessing you're laughing at something that's not differential equations? Okay. Gotcha. All right, so we're going to want to find the solution to the following initial value problem. 4 times the second derivative of y minus 8 times the first derivative of y plus 3 times y itself needs to be equal to 0. We're given the initial conditions that at 0, I want my value of my solution to be 2. And also at 0, I want my derivative to be 1/2. And I never actually did this pictorially, but when we deal with second order, essentially what we're saying here is I want my solution to start out at, well, my independent variable 0, my solution is 2, but what is that 1/2 telling me? That the derivative is 1/2. Derivatives describe the what? Slope of the tangent lines. If I have a slope of 1/2, what direction am I heading in with respect to the y-axis? Up or down? Up. So essentially what this is telling us is that, hey, I want to start at 2 on the y-axis, and I want to start heading up, specifically at a rate of 1/2. But then how I change after that is described by this differential equation right here. So I guess 1/2 probably would be a little bit more shallow than that. That's essentially what the initial conditions are ensuring us here. But I want to find the solution. So is this a second order linear homogeneous differential equation with constant coefficients? Yes or no? See Malvern shaking his head yes. Yeah, absolutely. No trick question there. This is definitely the type of differential equation that I can solve, which means I need to find out what the characteristic equation is. Hopefully after today's daily quiz, we all know how to get it now, again. So what's the characteristic equation going to be? Yep. R squared minus 8r plus 3 equal to 0. And now I need to factor this or find the roots. So we got to factor this. If I do, I know I have to have a 3 and a 1 because those are the only two factors of 3. But then I got to combine them with factors of 4, which are either only 1 and 4, 2 and 2, or -1, -4, -2, -2. Or I guess we could have a -3, -1. Got to play some algebra games, but I can figure out what these are supposed to be. When I sit with this a little bit long enough, trust my algebra that I've done time and time again up to this point in my mathematics career, I can see that this will factor into 2r minus 3 times a 2r minus 1. So -1 times -3 gives me what? -1 times -3 gives me +3, which is what I'm looking for. If I take a 2, multiply it by a 2, what do I get? 4. If I take a 2r, multiply it by a -1, I get -2r. If I take a -3, multiply it by 2r, I get -6r. -6r minus 2r gives me that -8r. All right, but then this tells me my roots are what? Mm-hmm. 1/2 and 3/2. And even if you don't feel too comfortable with factoring, especially when you have a coefficient that's not 1 on that leading quadratic term, the r squared term, Just a reminder, what can you always default to? Yeah, quadratic formula. But yeah, don't apologize. Okay, they'll also get you these answers, just might be a little bit more work. Okay, it depends on how your brain likes to attack these types of functions. So now that I have the roots of my characteristic equation, I know what the general solution is to the differential equation. It's going to be a linear combination of e raised to these roots times whatever my independent variable is. I never defined it in the problem. I'm just going to choose x. So it'd be a constant times e to the 1/2 x plus another constant times e to the 3/2 x. But I wasn't just given a differential equation. What else was I given? Initial conditions, right? So I need to also make sure I choose the values of those constants, C1 and C2, so that I'm going to match up with those initial conditions. Well, since one of those initial conditions involves a derivative of the solution, I should probably just go ahead and calculate it and then plug in 0 for my x's and set it up so that the original function is equal to 2 and the derivative is equal to 1/2, and then solve for C1, C2. But what is the derivative of y going to be? 1/2 C1 times e to the 1/2 x plus what? So this is what the derivative looks like. So now I apply the initial conditions. So then I know for my solution, this should be equal to 2 when I replace my independent variable with a 0. And that my derivative should be equal to 1/2 when I replace my independent variable with a 0 as well. So this gives me a system, but I probably want to simplify it down a little bit. Just clean up some little calculations that I know I can do. Well, anything to the 0th power is always 1. So anywhere I see these e to the 0s, I can just replace them with 1. So I get a 2 times c is got to be equal to C1 plus C2. And then 1/2 is equal to 1/2 C1 plus 3/2 C2. Now I need to solve this system of equations for those two unknowns. How would you go about doing this? Substitution. That is usually the easier thing to do. So I have to rewrite one of these equations just to give it numbers so we can talk about them, 1 and 2, for the first equation that's in that list, and second. Which equation do you want to rewrite so we can use for substitution? First one. All right. How would you rewrite it then? Okay. So now we know this relationship between C1 and C2. I plug it into that second equation. And this gives me 1/2 is equal to 1/2 2 minus C2 plus 3/2 C2. So distribute that 1/2 through. You get a 1 minus 1/2 C1 or C2 and then plus 3/2 C2. Well, if I take a negative 1/2, add 3/2 to it, what do I get? I heard mumbles, but I couldn't understand them. So if I take -1/2, it's going to just be 1. You can also think of it as 3/2 and -1/2. I get 1 minus or plus C2. Apologize, 1 plus C2. All right, I need to solve for C2. I subtract 1 from both sides. It's going to give me that C2 is equal to what? I'll give you -1/2, which means then C1 is what? Well, we said it's going to be minus whatever the value of C2 is. So I said 2. Sorry, C1 is going to be 2 minus whatever the value of C2 is. So I subtract a -1/2. Just means I'm adding 1/2 to it. So it's 2 plus 1/2. 5/2. So the solution to the initial value problem is y is equal to 5/2 e to the 1/2 times x, but then minus, because it's a negative, 1/2 e to the 3/2 times x. And, you can always just do some quick confirmation. I'm not necessarily going to check that my first derivative matches up, but if I plug in 0 for my x's, this becomes a 1, this becomes a 1, so I'm left with 5/2 minus 1/2. 5/2 minus 1/2 is 2. Which is what we were hoping for, right? That was given to us in the problem. So we can do just a quick check. Okay, and to this type of differential equation, there's really not much more meat to it. Find a characteristic equation, and then find its roots. Those roots give you your solution. Really, the harder part is having to use that little bit of linear algebra, solving a system of equations to figure out what the coefficients are. So what questions do you have for me? All right. So what we've done is we've started with equations such as a times y double prime plus b times y prime plus c times y equal to 0. And if we feel pretty comfortable with how to find solutions to these type of differential equations, our next step is then to generalize it, right? Not all differential equations are probably going to have constant coefficients. Maybe it's going to be like what we saw with some of our stuff with first order differential equations, where there's going to be functions of our independent variable. So we want to generalize this as something of the form oops, that's supposed to be a prime. Something like this, where my second derivative plus some function of my independent variable times the first derivative plus some function of my independent variable times my solution is equal to 0. Now, what we saw with just this simple one above, where coefficients are constant, we never actually had any calculus techniques to figure out what the solution was. We just had to make a clever observation to begin with. And then we said, oh, once we make this clever observation, I was able to build some theory around it. Well, that clever observation came from, okay, we need to use some functions of e to whatever. But now that I think about it, it's going to be much more complicated because it was easy to get a characteristic equation. Before, if I just try, or not before, if I try to take that same approach, say, okay, well, it's e to some number times t. And I plug this in, so this would be r squared times e to the rt plus p of x times r e to the rt plus q of x times r equal to 0. What I end up getting is this weird mix of two different variables. And I could say, all right, well, then this equation will only ever be 0 when e to the rt is 0, but then I got to figure out what makes that equation on the left 0. But now how many different variables do I have? I have 2. I have to figure out what r is, and I also have to figure out what x is. And that's always going to change depending on what this p and the q are. They could be some really complicated functions. I'm not guaranteed to be able to find zeros for that. And if I do, it's going to be a very complicated process, most likely. So we're not going to be able to just take this direct approach. We actually have to look at these a little bit further. And what we have to do is say, okay, let's not go straight for the solution. Let's try to understand a little bit more about this problem. Figure out what we can determine about the structure of something that looks like this. That second derivative of y plus a function of x times the first derivative plus another function of x times the solution equal to 0. And then maybe once we understand a little bit more about the problem, the theoretical framework around it, then that's going to show us the way we need to approach actually getting the solution. And this is what we do more often than not in differential equations. Finding the solution is extremely hard, but it's made much easier once we really understand the problem. So we're going to have to get a new way to look at this type of differential equation. And so the first thing that we do is say, okay, well, notice down this left-hand side, that's just an equation. And, or sorry, it's an equation, is a function. Specifically, it's a function of y. Because what it's telling me to do is say, all right, the first thing I do is find the second derivative of y. You give me y, I find its second derivative. Then I'm going to add that to some function that I predetermined times its first derivative. Again, two things that, one thing that's given to me, one thing I can calculate if you tell me what y is, plus another function times, again, what you just gave me. So I can actually rewrite this in the sense that this is just a function of y. Now, one of the things we like to do to help us recognize, especially in differential equations, that we're talking about this is a function of the solution of a differential equation is we're not going to use that parentheses function notation, just to try to help us differentiate a little bit, because this function L is still a function, because it does exactly what we described. It takes whatever that y is, finds its second derivative, adds it to p of x times the first derivative of that y, and then adds it to q of x times the function y. So the differential equation can be rewritten as the following. It's a nice little, this function's got to be equal to 0. And when we do this, we actually open up a lot more possibilities because you spent most of your algebra pre-calculus finding out roots for quadratic formulas or different polynomials. You find roots for equations, and one of the biggest things that you can study is what makes functions zero. And this is part of the reason why, is because we realize whenever we reshape these problems, we can usually reshape it to be functions equal to zero. Once you get that, it opens up a lot of doors. You can do, when you get to the high level, trying to remember that field of functional analysis. Anyway, something called fixed point theory. So it's different techniques, and it's just essentially what properties of this function L do I need to be able to guarantee that I will find a root? And what that guarantees me is then I'll be able to find a solution to this differential equation. Again, I might not be able to know what it is through that process, but at least I'll be able to guarantee that there is something there. So it would be worthwhile to go through and try to maybe do some calculus or some other high-level techniques. One thing that we'll learn about a little bit later on, Laplace transformation, Lagrange transformation. Can't remember the L word. I think it's Laplace. We'll learn about that. And it's, again, this same idea of we view this differential equation as a function. And when I treat it as a function, we can actually use some other techniques to solve it. That's a little bit down the road. Okay. First thing I'm going to do is tell you a nice little theorem. And the theorem is going to say, I can guarantee you that you will find a unique solution. We'll come back and revisit this a little bit later. But it's going to say the following. Consider the following initial value problem. So we have the second derivative of y plus some function of x times the first derivative plus some function times y is equal to g of x. So in this case, I'm not even going to make it homogeneous. Could be homogeneous, but it could be not homogeneous. So I'm even opening you up to a wider class of differential equations. And you have the initial conditions that y of x naught is y naught and y prime at x naught is y prime naught, where P, Q, and G are continuous on an open interval. Which we're going to refer to as I, that contains that initial starting point x naught. And what I can guarantee you is that this problem will have exactly one solution. And that solution will exist on that entire interval I. So we had a similar statement like this for just first order in initial value problems, right? We were guaranteed a unique solution in some range around the initial condition. However, we kind of were already guaranteed it because we found what the solution will look like. And we can prove this, but really for us at this point in time, we don't have enough tools. Why am I guaranteed that there is going to be a solution? And then, even if there is a solution, how do I know that it is unique, that there are no other ones? And really the only condition, I mean, similar to what we saw for initial value problems, the biggest thing is that we need those coefficients. So this coefficient function, this coefficient function, this coefficient function, just to be what? Zero, continuous. They just need to be continuous functions. Why does that? Why do you care about it? So we won't be able to prove it right up front, right? It's just a little bit out of our purview. But what we can do is say, all right, well, now that we have this kind of little supporting crutch, what happens if we do just assume we do have the solution? Okay. And if we have the solution, what can I do with that solution? What does that tell me about this differential equation in and of itself? Okay. So the first thing to recognize. So let me do this. When we were working with just the second order linear homogeneous differential equation with constant coefficients, how many solutions did we actually have? If I don't have initial conditions, how many solutions do I actually have? Well, that's if I have an initial condition. How many? An infinite number. So for the differential equation itself, there's always an infinite number. Now it's infinite because there's this constant multiple that I get to choose, and that can be any number. And since there's an infinite number of real numbers, there's an infinite number of solutions. So the differential equation itself is not going to ever be able to guarantee me uniqueness. The differential equation will only be able to guarantee me existence of a solution. So what makes it unique? When I consider an initial value problem, what makes it unique? Not the solution. I couldn't understand that last mumble. Yes. But how do we define the interval I? That's the question. Where does I come from? It's an open interval what? Can literally read it off to me. It's an open interval what? Contains x naught, contains my initial starting point. So really what's giving it to me is the initial condition itself, right? Which contains x naught. And once I establish what x naught is, then I can do that interval I. But it all stems back to just that initial condition. So the differential equation will always give us this general solution. The initial condition or conditions will restrict the general solution to a unique one. So the uniqueness is pretty much covered on its own, right? Initial conditions give us uniqueness. What is the bigger thing that we want to make sure that we're always guaranteed that we have? That it exists, yeah. That there is a general solution. Once I have a general solution, then it's guaranteed that I'm going to get uniqueness once I apply initial conditions. So we never have to worry about considering initial conditions, just the differential equation. And that's where we're going to start. First things first, think about how we were solving these second order differential equations. We had solutions. And was there just a single solution that we started with? Well, no. We had two usually, right? We identified two. So first one was e to the RT and then negative e, or e to the negative RT, or sine and cosine, depending on what the basic differential equations that we looked at. And then we took those two basic solutions and we made some linear combination of them, which is how we get this. C1 times one solution that we find plus a constant multiple times another solution that we find. So we can find two solutions, add them together, add constant multiples of them together, and we're guaranteed to have another solution, is what we've already kind of established. So let's formalize that a little bit more. So theorem. If y1 and y2 are two solutions, of the differential equation, so just some linear function of y, which we're just going to try to always assume for points or this discussion in the class, that's the second derivative of my solution plus some function times the first derivative plus another function times the solution. And I want it to be equal to 0. So we're just going to assume homogeneous. Really, it can be non-homogeneous. It works well for as well, but not as easy. There's a caveat to it. But we're not going to worry about that. But then the key thing is the linear combination. Is also a solution, and this is true for any constants. And then just a quick quiz of your math notation. This little last bit that I wrote out. C1 comma C2 symbol, this weird looking R. What is that representing? What's the statement? So C1 and C2 are elements of the real number. Yep. We already saw this in practice, but we explicitly stated what the two basic solutions were, right? What y1 and y2 are. In this case, we're not saying exactly what they are. We're just saying we have them. And it's actually pretty cool because we can prove this. It doesn't require too much to do. If I can just get a new page. So whenever we do proofs, we make assumptions. And it's the assumptions that were given in the statement of the theorem. So I know I have a differential equation. L of y, which is equal to y double prime plus some function p times the first derivative plus a function q times the second derivative. We're going to assume that y1 and y2 are solutions to the following differential equation. So just setting that function of y equal to 0. Essentially, there's zeros for this function, capital L. Once we have that, we're going to let C1 and C2 be elements of the real numbers. And with this, we have all the different working pieces that we needed from the statement of this theorem, right? Needed two solutions to this homogeneous linear different second order differential equation. And we're going to say that it's linear combination, any linear combination of those two solutions for any constants that are real numbers should also be a solution. So once I set up all of this work here in my proof, then my goal is to show that when I plug this linear combination of these two solutions into the same function L, if it is a solution, it should become what? Become 0. Because then this linear combination also satisfies the differential equation. All right, well, let's work it out. What the linear function L tells me to do is, whatever you give me, take the second derivative of it. Add it to P times the first derivative. And then Q times the function. Now look at this. Derivatives, well, I can use the sum or difference rule. Distribute those derivatives over addition. But then C1 and C2 are also constants, which I can pull constant multiples out of differentiation and multiply them back later. Which means if I'm taking the second derivative of any linear combination, well, distribute the second derivative over the addition, pull out the constants, and take the second derivatives of what you can take second derivatives of. Which just becomes the first solution, second solution. Well, similar story will happen there with the first derivative. But I'm still multiplying this by E of x. And I have this Q of x times C1, Y1 plus C2, Y2. All right, well, my goal is to show this is 0. I'm headed in a good direction. Because since I know Y1 and Y2 are solutions, if I consider that linear combination L, that function L, input is Y1, what should that be equal to? It's a solution. Should be equal to 0. 0. Same thing with Y2. Which means, thinking back to how we define this function L, if I can rewrite this or see appear the second derivative of Y1 plus P times the first derivative of Y1 plus Q times Y1, that linear combination of those three terms, I know that it's going to be equal to 0. Same thing for Y2. Still going to be equal to 0. And do I think I can probably get that from what we have written here? Absolutely. Distribute the P and Q through. Oops, I don't want to be in blue still. and then rearrange all these terms so I get my y1 terms together. Also think of it as, look at each of these terms that have a constant C1. Factor out that common factor of C1. If I do that, I have C1 times the first derivative or second derivative of y1 plus p of x times the first derivative of y1 plus q of x times y1. Now I go through the terms and factor out a C2. I get a similar statement, but with my second solution. And looky here, inside these parentheses. That's just what the output's supposed to look like if I plugged y1 into this function L. And then similarly for the second. What would happen if I plug y2 into the solution, or into the function L? But because y1 and y2 are solutions, L of y1 and L of y2 have to be what? Zero. Which means this is just C1 times 0 plus C2 times 0, making it all 1. Sure. So because y1 and y2 are solutions, I can now guarantee you that any linear combination of those two solutions that I plug into this differential equation will also come out to 0, which means any linear combination of y1 and y2 are also 1. Well, that's 0. They make the differential equation 0, meaning that they are what's for this differential equation. Solution. Since those constants C1s and C2s were any real number, we've gone out, or we've finished proving what we wanted to prove, meaning that we are done. So, all right, well, first things first, we have two solutions. We know how to get infinitely met. But what is the key assumption there? What was that? Yes, in a sense. What did we have to have for this proof? What did we have to assume that we already have? Two what? Two solutions. So, as long as we assume we have two solutions, we know we can get as many solutions as we want. But we still have to have two solutions. All right, well, that's kind of chipping away at this big wall that we have in front of us. So now I just need to be able to find two. Once I find two, I've got everything else because I now know all I need to do is make a linear combination. Well, finding those two solutions, it's a little weird. It's still kind of difficult. Okay, so maybe instead we go back and say, all right, we need to be able to find existence of solutions. So as long as there are one, we get a general solution. So we do have infinitely many. But then the second statement was saying, okay, the initial conditions are what's supposed to guarantee us that we actually have a unique solution. So if I can't really do anything with that first one right now, that's probably a good question to try and answer. Intuitively, we assumed initial conditions should make it unique. We should probably investigate why. And then through that investigation, maybe something's going to appear that's going to allow us to also glean some information to what solutions are supposed to look like. And then through that, I might be able to find what the solutions Y1 and Y2 are. It doesn't seem like an obvious path up front. Absolutely not, right? We usually want to be very direct, and how you're kind of taught a lot of things is very linear. But do you think when you actually get out into the real world, no matter what you're doing, differential equations, working in corporate America, being a social worker, whatever the heck you decide to do, you think it's always going to be very linear for you? No. Hey, whenever you hit a brick wall, pivot. Work on some other things. Figure out, okay, once I start getting a better understanding of the entire structure of the entire picture, then I can come back to this big brick wall and say, wait a second, are there actually some handholds there now that I can start climbing over it? Or, hey, is there a weak spot now that I can see that now I can break this wall down? So let's at least try to answer that uniqueness part. So you give me two solutions. I know I can always find a general solution. There's infinitely many solutions. But from that, can I actually guarantee my intuition that there's only going to be a unique solution? I think I spelled guarantee right. Sorry, let me see unique solution to an IVP. So can we always guarantee a unique solution at least? Right, we said as long as I have two solutions, I can get a general solution. All right, well, with that general solution, which is just some linear combination of the two solutions that we assume that we have, well, can we still actually guarantee uniqueness? And there's only going to be one function that's going to go through those two initial conditions that we have for second orders. Well, if the initial conditions are just going to be that solution at x naught is y naught, and that my solution's derivative has got to be this, then for the two solutions, y1 and y2, we must have that their linear combinations are also going to satisfy it. And then just really quickly, we're still also covering in this general sense, the cases where we're looking at just y1 or just y2. Because if I want to consider just the solution y1, what can I set this constant to be to get rid of y2? 0. It gets rid of the y2 part, and I'm just saying, hey, I'm looking at when some constant times y1 at this initial value and some constant times the derivative of y1 at this initial value equal these two values that I get from my initial condition. Similar story for y2. I can set the constant c1 to be 0, and that way I'm only considering y2. So I'm considering both of those cases plus an infinite number of other ones. Well, this ends up creating, again, another linear system. We saw this happen. I can solve it potentially. I could do substitution. But what is going to guarantee me that I'm going to have a solution, and specifically a unique solution, that is for C1 and C2? Because we're assuming that Y1 is known and Y2 is known. So I also know their derivatives as well. And then I'll know what the function values are for the Y1 and Y2 and its derivatives. So I have to use linear algebra. Turn this into a matrix system. So I can take that linear or that system of equations and turn it into a matrix. This would create the same equations, because if I do this matrix multiplication, first row times first column, why not Y1 times C1, Y2 times C2? And that should be equal to the very first entry, Y naught. Similarly for the derivatives, Y1 prime times C1, Y2 prime times C2 equals to what my derivative needs to be equal to. And then to be guaranteed that this system will have a unique solution, i.e. unique values for those constants, C1 and C2. There's a particular matrix that I have to look at. Well, what's the only matrix I have there? I ruined it. It's a matrix. A 2x2 matrix with all the y's, right? Well, we guarantee that this system has a unique solution. What was the fact that I need about this matrix? It deals with the determinant. Yeah, determinant can't be equal to 0. If the determinant is non-zero, it's going to have a unique solution, because I know that matrix will be invertible. And if it's invertible, I can multiply by and get the one and only one vector for the constants. So then we get to say that the solution, this general solution, when we fit it to that initial value, the initial conditions, its initial value, is going to be true if and only if the determinant is not equal to 0. But this is a nice little simple 2x2 matrix. I can tell you exactly what the determinant is. It's Y1 at this initial point times the derivative of the second solution at this point minus Y1 prime times Y2. So as long as, whenever I find these two solutions that I use to then make my general solutions, as long as this combination of them and their derivatives isn't equal to 0 at my initial starting point, x naught, I'm guaranteed what? Unique solution to the initial value problem. I want to make that clear. Unique solution to the initial value problem. And we can actually, again, sum this up in a theorem. So we're going to suppose that Y1 and Y2 are solutions. to that same different general differential equation. Try to erase. And after we find these two solutions, then we're going to assume that we're also going to apply the initial conditions. Then it is possible to choose. What was that? 2x. Oh. Thank you, thank you. If we apply initial conditions to whatever the solutions are for this differential equation, we know that then we can find two constants, C1 and C2, such that any linear combination, or there is a linear combination of those two solutions with these constants, that satisfies the differential equation and those initial conditions. If and only if. That's called the Wronskian. Is non-zero at x naught. Whew. Good bit of writing, but it's all there. Let me try to keep it all on the same page. So I'm not too familiar with who Wronskian is, but he was the first one to identify that I can change something like this into a system, look at that determinant, and then, hey, I just need to look at this calculation. And as long as this is non-zero at that initial starting point for my independent variable, then, hey, I know I'm going to get a unique solution to this initial value problem. Well, let's confirm that that's actually working, because even though they're nice little constant coefficients, we've already worked with differential equations that satisfy this. And we've also worked with differential equations that had initial conditions applied to them. So go back to the example that we did at the very beginning. We had 4y double prime minus 8y prime plus 3y is equal to 0, with y of 0 is equal to just anything. I'm going to say y naught. And y prime is 0 is y prime naught. Sorry, x0. So instead of nailing down what the initial conditions are, I'm just going to say I give you some. Well, will I be guaranteed a unique solution now? Is the question. We know before when it was what, 0 and 2 and then 0 and 1/2. If my memory serves me correctly from an hour-ish ago. Well, do we actually need to specify what they are to guarantee what a unique solution is? Well, the two solutions that we found were, well, y1 we can just set to be e to the 1/2 x and y2 e to the 3/2 x. So the question is, if I apply these initial conditions, will I be guaranteed a unique solution? Well, as that theorem says, just find the Wronskian at the initial condition. Well, to get the Wronskian, I also need the derivatives of these two solutions. Well, that's just 1/2 e to the 1/2 x and 3/2 e to the 3/2 x. So then I calculate the Wronskian of these two solutions, which means I take y1, multiply it by the derivative of y2. Subtract it. I did subtraction up here, right? Good. Subtract it from the derivative of y1 times y2. This creates my Wronskian. I can simplify this down to 3/2 e to the 2x minus 1/2 e to the 2x, giving me just e to the 2x. So then when I consider this Wronskian, all I need to do is say, okay, if I plug in x0, so the Wronskian of these two functions at x0, well, that's just going to be e to the 2 times whatever x0 is. You can give it any initial starting point for your independent variable. This is what the Wronskian is going to calculate. And the one thing I want to make sure, so I get a unique solution, is that the Wronskian is what? Non-zero. Yeah, perfect. Non-zero exactly at x0. Think about these exponential functions. Yeah, it can't be 0. Exponential functions will never be 0. So it doesn't matter what starting point on for this independent variable that you give. You're always going to be guaranteed that that Wronskian is going to be positive. What is it? 4y double prime minus 8 prime, 8y prime plus 3y equal to 0 with any initial condition. And I'll stop there. So the Wronskian is a pretty important calculation. That's what's actually going to define uniqueness. Again, we still have this kind of prevailing issue. What are we still assuming? We have two solutions. right? Once I have the solutions, then I'm starting to figure out what I can do with them. But the question is still, how do we get those solutions? Now, the first thing we're going to address is that this Wronskian, even though we can do this calculation, actually, we don't really need to do the Wronskian. There's actually a better way to figure out what this value is. We still want to make sure the Wronskian is not 0, but we can do the calculation in a different manner through something called Abel's theorem. But that's going to be something that we do after spring break. Okay. So this Friday, you have a pretty big project, right? You have all day Thursday and all day Friday to do it. So it'll give you 48 hours. So what I'm going to do is I'm going to guarantee you that you definitely have a free 50 minutes on Friday to be working on that project. Okay. So for differential equations, we will not be meeting Friday from 2 to 2:50. Use that time wisely. If you want to go ahead and finish the entire project tomorrow, then that just means you don't have anything to do for me in differential equations on Friday. Okay? Do what? Yeah. What was that? Sorry? Writing everything out nice and neatly, 2 to 3 hours. And that is, again, with the same idea that I was telling y'all on Monday, if you're well prepared, right? If you're having to go back and look up how to find solutions, and what an integrating factor is for first order differential equations, then it's probably going to take a while, right? But if you remember all that stuff, you refresh it, and then start attacking the problem, it shouldn't take you more than a couple hours, 3 hours. Okay. And then there will be a new model. It's really similar to what you worked with. But the biggest piece of advice that I have for that problem is don't overthink it. I pretty much described to you, not necessarily in mathematics symbology or symbolism, right? But I tell you exactly what to do. If things are interacting with each other, how they're interacting, and then you have to translate that to kind of some simple mathematics, but it's not too difficult once you translate it. So when I've done similar questions like this before, that's usually where people got tripped up. It wasn't ever actually the differential equations part. It was the transferring it from words to mathematics notation. Okay. But if you have questions, what can you always do? Ask and email. Okay. Even though I won't be here in 302 from 2 to 2:50 on Friday, I still have my email connected to my phone. I will see it come in and I will answer as soon as I can. All right. Now, if you're emailing me at 10 o'clock on a Friday night, I might not be too happy. I might actually even sleep, and depending on how much this week takes out of me. So, starting on early so you can guarantee to get a response from me very quickly. All right. I guess usual spiel. If you have questions for me, feel free to stick around and ask them on whatever. Otherwise, feel free to get on out of here. Stop the recording.